Good morning, all. Are you able to hear my voice?
Yes, sir.
Last class we discussed about the basics of the Navier-Stokes equations. We'll go ahead with that. I will share the screen. Can you able to see the screen right now? The title on 10 fluid mechanics. One is from
Yes,
your
sir.
okay, fine. Okay. Last class we discussed about the basics of the Navier-Stokes equation. This is a great equation where it can demand for $1 million, almost about 7 crores money, if we solve the solution of it. Of course, you can try. The problem is also so complex. It is not so easy to handle such type of complex equations. For example, even if you pour a water from a bottle or any kind of a vessel to a cup, the shape it takes is very indifferent. It will never repeat its shapes. It will never repeat its size. Of course, the size of the bottle or the dimension of the cup, whatever you are using, may be the same, and the volume occupied by the liquid, maybe water or any kind of a liquid, also may be the same. But thing is that when you pour, the how it try to occupy the position or the volume of the space we can call, it differs. Some kind of a bubbles may form, some of them may spill it out, or some of them may be having a great thing in such a way that where they could not be able to solve through the set of the equations, it should behave like that. It is not like a one-dimensional problem or two-dimensional problem, even not a three-dimensional problem of that kind. Of course, I am not saying it is impossible, but it's a difficult task. It's a complex issue of solving such type of an equation. Okay, let us see that the Navier-Stokes equations and maybe the possible solution for the case of a flow through a cylindrical pipe, that we have to do that at least. Okay. Here, what happens here, last class when we were discussing about this is the preamble for the Navier-Stokes equation. Conservation of mass should be there. Mass neither be created, mass neither be destroyed. That gives us the continuity equation. So you have seen here actually in the sense the integral of under continuous volume, they can call actually rate of change of dou rho by dou t in terms of dv plus the same thing with surface integral with v dot dn must be equal to 0. Means the mass neither should be created, mass neither should be destroyed. Whatever the mass which is there, either maybe for liquid or maybe any of the solid of that kind, may have the chance to change its phase from gaseous to the solids or to the liquids or maybe vice versa of that kind. In general, we can write this conservation of the mass as the rate of change of d rho by dt or del rho by del t as a function of its volume in continuous volume. What we are expecting here must be equal to the mass which is flowing in and the mass which is flowing out. This we discussed earlier. As a continuity, I put this slide back once again. Means to derive this differential equation, differential conservation equation, we are imagining in such a way that shrinking this entire volume to an infinitesimal size, infinitesimal small size, not the larger volume. Okay, let us choose a small dimension in such a way that dx times dy times dz is the volume which is occupied by a mass. How that the flow can happen? The flow will happen in such a way that the total mass which is entering into the region must be mass which is leaving out. If the volume which is entering in or the mass which is entering in, if it is equal to the mass which is going out, instead of mass they can call it as also a flux, or maybe the quantity or amount of the water or amount of the fluid which is coming in must be equal to the amount of the mass fluid which is going out, then no net mass inside the volume element what we can call. If the net flow is more compared to that of the outflow, certainly the accumulation will happen. You can't expect that outflow should be more than that of the inflow at any cost of that kind. Being this, we got this divergence theorem actually, okay, where the volume integral must be linked with the surface integral. This also have discussed last class, may not be the just previous class, before that at least. Means the volume integral of this one is equal to the surface integral of the g times into dp. We can also write this in a different way. It led to the continuity equation where rate of change of density and plus the divergence of del dot of v must be equal to 0. This equation is for the compressible form of the continuity equation, since we have not assumed the incompressible flow. No liquid is incompressible. Since all gases are compressible, not assumed as the incompressible flow. It is valid at any point in the flow domain. It is It is valid at any point in the flow domain of that kind. Being this, we obtained this equation. I will not repeat actually. This rho u at the center of the right face must be equal to rho u plus del by del x of this value 1 by 2 5. Higher order terms we will ignore. Maybe towards left side, this is the case. Towards the right side, this is the case. And if you go for left face, right face, top face, bottom face, front end, and the back end, six set of equations will come. Means a small box which is assumed as the control volume, which is centered at P, is used for the derivation of the differential equations for the conservation of mass in Cartesian coordinates. The red dots are showing the center of each face. Center of each face. Okay. If this is being this, what happens is that if you go for the net equation, the total flow which is coming in should go out. Okay, left face the total sum, bottom face the rear face. Then we got this equation for the continuity: rate of change of del rho by del t plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w. These are the three components along the x, y, z direction corresponding to the speed of u, v, and w respectively. This is the time derivative. This is the space derivative of the time. This divergence operation in Cartesian and cylindrical coordinates can be represented what we have shown in the black colored box. This I stopped at that time last class. Okay, and we can also write this in the differential equation in such a way in terms of the linear momentum as the Cauchy's equation. Cauchy's equation is the one where it gives us the total sum of the net flow must be equal to the integral of the continuous volume rho g times dv plus the surface integral of this is the tensor. This I will introduce right now. Okay, and the integral of del, this must be equal to del by del t of rho v plus rho v dot times v dot delta. Or you can also resolve this into this is one is due to the entire body, this is due to the surface, two components. These two forces, this is the first term is for this one, second term for this positive component of the stress tensor. They will call it as a sigma x, sigma. Stress tensor is nothing but the component of the total force which is acting per unit area. Force acting per unit area. Stress tensor we can call a tensor. In Cartesian coordinates, on positive side you can expect right side is positive, top is positive, and the front end is positive. The same values you can go for the negative components, for example left side, okay, then the rear end, then maybe the bottom side. Okay, this is represented by dx times dy times dz of that kind. This is how this stress tensor can go for this phase. Sigma xz for this plane, sigma of xy for the top, sigma xx along the direction of the xx. Okay, this is the tensor sigma xy vertical, sigma xz towards u, or if it is negative, minus a sigma xz minus a sigma xy minus a sigma xx of that kind. Okay, we stop at this point. Let us see that if this is derived in an infinitesimal contour, actually we have added up all those things like inflow must be equal to outflow, where we got the rate of change of the x momentum within the control volume. We got del t by del by del t of rho u times dv. This must be equal to del by del t of dx into d by dz. This is the volume element. dv you can call the same case. The same case. This net outflow, particularly, we got this expression. I have not shown this actually. For example, if you take including the gravity vector which is acting downward, is not necessarily aligned with any particular axis, because it is always trying to put it downward. Okay, put it downward, and there are three components of the body force they can call, which are the body forces they can call body forces which are acting on infinitesimal fluid element. Being this, we got this relationship with the Cauchy's equation. This I am repeating actually. Okay, this is along one x direction, sigma xx minus this value. This along the positive direction. We can add the flux inflow to the outflow should be the sum of these two along the x, some of them along the y, some of them along z, either inward or outward. Okay, means to say that the total flux should be del by del x of sigma xx in terms of tensor, del by del y of sigma yx, okay, or xy also you can call del by del z of the zx, or you can resolve into rho times gx plus this is the equation what you are expecting. Being this, If you add all of them put together, we'll get the Cauchy's equation. What is the Cauchy's equation? What we got? We got this Cauchy's equation as del by del t of rho v plus del dot of rho times vv vector plus rho g. That must be equal to rho g plus del dot of the tensor. This is the sigma ij is the tensor with the 9 component we can call. Okay, with this vv what we are expecting, we can write into the 9 components along u one phase, u of v along the vertical, u along the w. This one case means along u with the same phase, front phase, along u with the horizontal phase, u with the vertical upward phase. This is the v with u v w, w with u v w of that kind. This is the outer product of the vector v with itself is a second order tensor. Okay, that is why the product shown in the Cartesian coordinates and is illustrated as 9 component here. What are the 9 component we got it? We can also write this Cauchy's equation as an alternative form, the same that thing what we got it earlier. This is the preamble for our Navier-Stokes equation. Okay. Along with that last class, we discussed about that how that Navier-Stokes equation can happen for the rho v must be equal to 0, and also for the forces, 3 forces which are acting, either frictional force or maybe the volume force or maybe the gravitational force of that kind. That is this is the beginning. You can start from this end actually, because this I discussed long back. That's why I repeated the Cauchy's equation or an alternative form of it here, either this Cauchy's equation or the alternative form of the Cauchy's equation here, what I am showing in red color, is not useful much as such in the form what it is representing right now, mainly because the stress tensor sigma ij contains 9 components here. This is sigma ij here, or maybe here what you are expecting, it contains the 9 components. Out of the 9 components, 6 components are independent because of the symmetry. How that symmetry can go, maybe I will show you here. You remember here, I will come back again. This is the sigma ij. Sigma ij can be represented as sigma xx, sigma x of y, sigma xz along z direction, sigma y along x, sigma y along y, sigma y along z, sigma z along x, sigma z along y, and sigma z along z direction. Except the principal diagonal elements here. Okay, sigma xy and sigma yx are symmetry. Sigma zx and sigma xz are symmetry. Sigma zy and sigma yz are symmetry. These 3 plus 3, these are 6 tensors which are mirror image to each other. Okay, out of that sigma is 9 components, 6 of which are independent because of the symmetry. They are not depending one on each other. Maybe one along the forward direction, one along the reverse direction. One will be from towards the top, one should be towards the bottom. One should be near to you, one should be away from you, of that kind. In addition to the density and the 3 velocity components here we are having a density component and also 3 velocity component. Density is 1, velocity is 3. In addition to the density and velocity components, there are 6 additional unknowns here. 6 additional unknowns means together how many becomes total? There should be total 10 unknowns are there. In Cartesian coordinates, the unknowns are the rho, u, v, w. Okay, this is under suffix. You can go sigma xx, sigma xy, sigma xz, sigma yy, sigma yz, and sigma zz. I don't know whether you got it there. Okay, here where I should go here. Sigma xx, sigma xy, sigma yy, sigma xz, sigma yz, and sigma zz. Leave it the lower components of the 3 because they are mirror image to each other. Otherwise, even if you take from the top here, you can leave the upper matrix also. They are mirror. Total 10, there are 10 variables. Means being this, there are 10 unknowns. There are 10 unknowns actually. We have to solve the equations to obtain the solutions for the 10 unknowns actually. Okay, value of sigma should rho should be known, value of u should be known, value of v should be known, w, then the stress tensor along xx, xy, xz, yy, yz, and zz. What we discussed earlier was that with only 4 equations so far, one is the continuity equation. There is only a single equation, okay, where density does not change with respect to time actually. In the sense, mass neither should be conserved, mass should be conserved, neither should be created, nor should be destroyed. Under the Cauchy's equations are having 3 forms: 1, 2, 3 of that kind. Okay, 3 of that kind. Three unknowns, 3 equations. Okay, of course, To be mathematically solvable, the number of equations must match with the number of the unknowns. If there are two equations, there should be two unknowns. It is easy to solve. If there are three equations, we should have a three unknowns. Otherwise, sorry, if there are three unknowns, we should have a three equations to solve. If there are three unknowns, if you are having a two equations, it is difficult to solve. What normally they will do, they will make a guess for one variable, and being that variable as the guess within the boundary condition, they can estimate the other two, or maybe arrive for the other two. And thus, we need six more equations here. See, so far we solved for four equations, one for continuity and three for the Cauchy's equations. But we need, because of the this six variable quantity, we need another six unknown equations actually. Six equations. These equations are called the constitutive equations, and they enable us to write the components of these stress tensors in terms of the velocity field and also the pressure field. Means this is sigma x, sigma xy, sigma yz, sigma yy, sigma yz, and sigma zz should be represented in terms of the velocity field as well as the pressure field. Sorry, velocity field and the pressure field. That we'll see that how we can do that. The first thing what we do is that separate the pressure tensor and the viscous stresses. Okay, separate the pressure tensor, separate the pressure stresses and the viscous stresses. The pressure will, the viscous stress is nothing but equal to the viscosity, and pressure is only the pressure which is acting to the force which is acting on it. When a fluid is at rest, for example, the only stress which is acting at any surface of any fluid element is the pressure. That you are well aware, which is always acts as either inward and normal to the surface. Means assume that here pressure which is acting normal and pressure which is acting here from along this direction, which is normal to the one plane. You can call this plane. Okay, here the pressure which is acting, which is the plane. This is the one. This dot. Here the pressure acting on the top, but at the center dot is shown for entire surface. Here the pressure from the bottom surface, pressure towards inward. This P. Okay, this is the one for the radiant they have shown here. For this one, how that it is acting actually. Being this, the regardless of the orientation of the coordinate axis, either tilted or whatever you expect, always x, y, z should be the perpendicular to each other. For a fluid at rest, the stress tensor reduces to the same stress tensor is sigma ij with the 9 component. It reduces to the 3 components only along the principal diagonal elements. The symmetry that exists along the anti-principal diagonal elements should be the zero values. Value should be zero. Means P is same as in the whatever the P we are using here. P is the pressure actually, is same as the thermodynamic pressure what we are expecting from the ideal gas law. PV times is equal to nRT. This P is related to the temperature. Of course, there is no doubt, and it is also related to the density through some type of an equation known as the ideal gas law. Okay. Here you can, this further complicates a compressible flow fluid analysis, because we introduce at another term known as the temperature. PV is equal to N times RT. Okay. PV is equal to N times RT. N is the constant. N you can call as number. V is the volume. R is the real gas constant. But the temperature is an unknown parameter. I think here. This new unknown, whatever the temperature term actually, this requires another equation. There is another differential equation in the form of the energy. Temperature, with reference to temperature, energy will also change. Here, remember that being Navier-Stokes equations, we need so many things to solve. Being this, the stress tensor can be resolved with the 9 components, can be converted to the only 3 components, because these 6 are they are having a symmetry. 3 of them are having a symmetry with each other with 6 variable to a great extent. Means otherwise you can cancel one after the other by matrix method. Okay, we will lead with the only principal diagonal elements. Means to say that we need only the 3 unknowns. We only need 3 unknowns to solve the 3 equations. This you have solved at various times. Being this, if the fluid is at rest, the same equation here, the fluid is at rest, this equation converts to this to the matrix along the principal diagonal elements. Is where tau ij here is called the viscous stress tensor. Tau ij, tau is nothing but the stress they can call. Tau being the viscous term, tau suffix ij known as the viscous tensor. What happens when a fluid is moving instead of stationary? Pressure still acts inward normally. Here pressure acts inward normally. Okay, but viscous stresses may also exist. If the fluid is at rest, viscous term is 0. If the fluid is moving, viscous stress acts. Then one can generalize this equation, fluid at rest as the move for the moving fluids. Okay, the same expression must be equal to, along with this, there should be an additive matrix as tau xx, tau xy, tau xz. It is the shear stress. Okay, stress tensor. This is the shear stress tensor. Okay, tau yx, tau yy, tau yz, tau zx, tau zy, tau zz. Here, this tau ij, which is called the viscous stress tensor, or we can also call it as an deioteric stress tensor. This is the only the term which is used. You remember it as the viscous stress tensor to a greater extent. Mathematically, we have not helped this situation. See what we have done. These 9 components we have not done. These 9 components are there. Anyway, these 9 components are there, but we added with this. Mathematically, we have not helped this situation because we replaced these 6 unknowns. We replaced these 6 unknowns components of sigma ij with the 6 unknowns of the tau. 6 unknown of sigmas are replaced by 6 unknowns of the tau. Means if we replace the sigma to the tau, sigma is the shear stress to the deviating stress of that kind, particularly viscous stress they can call. Okay, tau ij, and added another unknown. In addition to that, we also added another unknown, which is known as the pressure, variable pressure. Fortunately, what happens? However, there are constitutive equations that expresses tau ij. Constitutive equations here. Sorry. Yeah, these equations, this set they can call it as constitutive equations. Okay, these enable us to write the components of the stress tensor in terms of the velocity and the pressure field. Here, our advantage here is that these dows can be represented in terms of the pressure and velocity field, change in the pressure and the change in the velocity of the fluid either along the x direction, y direction, and z direction. Okay, constantly expresses tau in terms of the velocity, field, and which are measurable fluid properties such as viscosity. Viscosity is a measurable one. Velocity is a measurable one. Actually, actual form of these constitutive relations depend on the type of the fluid, whether ideal fluid, non-ideal fluid, whether they can call it as Newtonian fluid, whether whatever may be the different types of fluids we discussed. Actually, it depends on the type of the fluid. If the fluid is an incompressible, okay, the fluid is an incompressible, we have no equation of the state. For example, it is replaced by the equation rho is equal to constant, and we can no longer define P as the thermodynamic property. If it is for incompressible fluids, rho is constant, being that P can be P cannot be used. No longer define the thermodynamic property. Instead of that, we define P in this equation here as the mechanical pressure. Mechanical pressure which is acting along x direction, y direction, and x direction, y direction, and z direction. Being this mechanical pressure, what one has to expect? We can see here in such a way. Mechanical pressure is the mean of normal stress acting inwardly on a fluid element. Mechanical pressure is the mean normal stress which is acting inwardly on a fluid element. If it is acting in normally on all the faces, here, top, bottom, actually, this mechanical pressure can be summarized as in terms of shear stress of the tensor sigma xx plus sigma yy plus sigma zz over 1/3. Means these are the three faces x, y, z over 1/3. Negative sign is mainly because the value decreases. Means to say that for a fluid at rest, the only stress on a fluid element is hydrostatic pressure. If the fluid is at rest, the only stress on a fluid element is that hydrostatic pressure is acting due to the gravitational influence downward against the buoyancy upward, which always acts inward and normal to the any surface. It is the inward, P is along the inward, normal to the surface. This P is along the inward, normal to the surface. P is inward, along normal to the surface. And the expression can be reduced as Pm is equal to 1/3 of sigma xx, sigma yy plus sigma zz. Beings. How we can go for the derivation of this Navier-Stokes equation for an incompressible flow, which are also an isothermal flow. How do you define actually? For a fluid, if it is said to be both incompressible as well as isothermal flow, if it is incompressible, density should not change, density remains constant. If it is an isothermal, mu remains constant. There is no change in the temperature. Okay, temperature of the system remains constant, maybe the exchange of the energy with its neighborhood. And being this, the mu is also constant. When you fall into the quicksand, earlier I told, like a dilatant fluid, faster you try to move, the more viscous the fluid becomes. Means for the dilatant fluid of that kind, if you allow the movement very faster, the fluid earlier it was an inertia. Because of its movement, it acquires the viscous property. It will sink into it. Okay, viscous stress here, viscous stress tau ij for any incompressible Newtonian fluid with a constant properties can be represented as 2 times this viscous property, this isothermal mu times epsilon ij. This tau ij can also be represented as a tensor in terms of matrix tau xxxy part you are expecting. This fine. This tau xx, the value of the tau xx lies in such a way 2 times mu of this del u by del x, rate of change of the flow of the fluid along the x direction with a speed of u. Along y should be with the two components, except the principal diagonal elements, where it can have along the x direction, along the y direction, along the z direction, the speed along u along x, speed v along y, speed w along the z direction. Okay, rate of change of the component of the fluid along that direction of that velocity multiplied by this term, this term. Okay, but the all other 6 elements are in such a way, rate of change v and u parallel to the x, sorry, perpendicular to the x, v and u, v of that kind. Here v and w accept the quantity of that kind. Here the along the x with y, along v with x, this is the same thing what you are expecting. These 9 components should be there. If you compare these two, del v by del x plus del u by del y, here it is interchanged del u by del y, first one, u and y, and v with x. Here also same case, del w over del x with del u over del z, except the z component. The numerator should not have the z component of it. Here del u over del z plus del w over del x, between del w over del y to del v over del z, or del v over del z. This is a nine terminologies tensors of that kind. Being this equation, this should be equal to, this is equal to the sigma ij. These two equations are rho times du by dt. We are using uppercase because it is the what we can call the derivative. It is called the Lagrangian derivative. They can call actually, sorry, total derivative they can call. This is not the partial derivative. Left hand side is the total derivative. Right hand side is the partial derivatives. Okay, the difference is that partial derivative is the derivative of that component only along the direction. Total derivative is the sum of all of them, but the total derivative is as a function of the time. This is as a function of the time. These partial derivatives on the right hand side are as a function of the spatial coordinates, either x or y or b, z. Del rho by del x plus this rho times gx can add up together, plus 2 mu times 2 derivative, mainly because if you solve this equation you will get actually del square u by del x square plus mu times del by del y of these two terms. But we should also know here in such a way, mu times del by del z of del w by del x must be equal to mu times del by del x of del w by del z. Okay, you can interchange also. This del by del z, del w by del x. Del w by del zx is vx. Del by del x. If this is a case, you can write, take the mu common. Del square u by del x square plus del by del x of del u by del y. This is the same terminology. Or plus mu times del by del x of this one, del u by del x plus del u by same case. Replace this with the operator. The Laplacian operator can go with the del square here, del square, okay, and this in cylindrical coordinates you can, of course this is Cartesian only, you can remember. The Laplacian operator here shown for the both Cartesian and cylindrical coordinates, which appears in the viscous term in incompressible Navier-Stokes equation. Being this, the same equation can be converted into rho times du by dt must be equal to minus del rho by del p by del x plus rho gx plus mu times del square of u, mu times del square of, or this can be, this is along the u direction. if it is along the v direction, same thing with y, along the y with the v direction, with w same case, or you can combine them together vectorially. Rho times dv by dt as a function of time must be equal to minus del p plus rho times g plus mu times del square v. That must be the constant value. Means this is the Navier-Stokes equation is the cornerstone of the fluid mechanics. This is one in pictorial representation how they can show cornerstone of the pictorial matrix. The Navier-Stokes equation is an unsteady, it is not constant, non-linear, second order partial differential equation. What you expect actually? Navier-Stokes equation is an equation which is an for the unsteady fluid and which is also a non-linear. It is a second order partial differential equation. This equation has four unknown quantity in the red color what we have shown. Three are velocity components and one is the pressure component. One is the pressure component. This is the velocity component either you put along the x direction, y direction, z direction. Yet it represents only three equations. There is no doubt here. Here three equations. These are three components since it is a vector equation. But obviously, what will happen? We need another equation to solve, make the problem solvable. With these three equations, it is not possible for us. See, with this actually, the fourth equation is incompressibility continuity equation, incompressible continuity equation, that is del dot v must be equal to 0. Being this is the continuity under the Navier-Stokes equation, you can, because this is the continuity equation. If you combine this continuity equation with the Navier-Stokes equation, the continuity equation, Navier-Stokes equations are expanded in Cartesian coordinates. I like x, y, z, and also in UVW as the velocity component. Incompressible continuity equation can be represented as del u by del x plus del v by del y plus del w by del z, that is equal to 0. Take that the x component, y component, and z component of incompressible flow in terms of the Navier-Stokes equation. Say same thing, rho times here, rho times what we get here, rho times del u by del t plus u times del u by del x plus v times del u by del y plus w times del rho by del z. This must be equal to minus del p by del x here, the gradient in the pressure along the x, plus rho times gx plus mu times del square by u by del x square plus del square u by del y square plus del square u by del z square. This is along the x. Along the y, what happens? What is the change you are expecting? Instead of u, you go with the v component. It remains here. Instead of x, the derivative should be y. Instead of here you again you replace this with the v component. I don't know, you got it, I hope actually. The u component will change with the v component along y, and instead of the rate of change of the pressure along x, rate of change of pressure along the y component. Of course, the same thing, the second term also not along the gravitational influence which is acting along the y direction. In z also, this is the same case. This is the first top equation is the incompressible continuity equation. Later three are the Navier equations, particularly incompressible Navier-Stokes equations along x component, along x direction, y direction, z direction of that kind. For incompressible continuity equation in Cartesian, that is in the Cartesian coordinate equation, Cartesian coordinates, in polar coordinates here, what you are expecting, 1 over r times del by del r of r times u along the r direction, 1 over r times del by del t of u of theta. You can represent r theta z as the spherical coordinates. These r components you can represent the three directions along. The same thing you can follow it up. Usually when they ask for either examinations for any of those things, either this method, the what I am showing here, Cartesian, or maybe the spherical coordinates of this kind you can use, either one or that of that kind. Here there is no need to much change actually. This is the same equation, it is converted into r theta phi, r theta z they can call, need not be phi of that kind, spherical coordinates. Being this, what are the applications of the applications and the problems of the Navier-Stokes equation? That is the case, there is a three-dimensional incompressible flow. If it is a three-dimensional incompressible flow, four variables or maybe four unknowns should be there. Out of the four, one is the pressure and other three are the velocity components. One is the pressure coordinates, it's not coordinate system. One is the pressure component, other three are the velocity components either along x or y or maybe z direction. Being four equations of motion, One is the continuity equation, that is del dot v is equal to 0. Being del dot v is equal to 0, three components of Navier-Stokes can come. Being three components of the Navier-Stokes, rho times del v by dv by dt, as in what type of an derivative? Total derivative they can call. These are the partial derivatives minus del p plus rho times g plus mu times del square v must be equal to constant, that is equal to rho times. Being this, there are two types of problems for which the differential equations, either continuity and Navier-Stokes, are useful. One is to calculate the pressure field here and pressure field for a known velocity. If we know the velocity, one can calculate the pressure field, or calculating both the pressure and velocity fields for a flow of known geometry and known boundary conditions. If a fluid is flowing through a pipe, then the geometry of the pipe is known, then it is easy to calculate either the pressure or maybe the velocity. Means pressure of the fluid or velocity of the fluid at any given amount of time or at any given point. Being this is a general three-dimensional, but it is for incompressible flow field with constant properties that require four equations to solve for the four unknowns. Four equations are required to solve for the four unknowns. One for maybe pressure, one three for the velocities of the chemical. Being this, calculation of the pressure, if we expect field for a known velocity field, the first set of examples involves the calculation of the pressure field for a known velocity, no doubt. Since the pressure does not appear in the continuity equation, because density will come into the picture, we can theoretically generate a velocity field based solely on the conservation of the mass. Depending on the mass of the fluid, one can have the general expression for the velocity. However, here what happens, the velocity appears in both the continuity equation and also velocity appears in continuity equation and also in Navier-Stokes equation. These two equations are coupled. Coupled means they are combined together. In addition to the pressure, which appears in all the three components of the Navier-Stokes equation here, pressure appears in all the three components, x component, y component, and z component, or maybe r theta components, yeah, del p by del x, del p by del y, del p by del z, right? Del p by del r, del p by del theta, del p over here somewhere, del p over del z. Because of this, since the pressure appears in all the three components of the Navier-Stokes equation, and thus the velocity and pressure fields are also coupled. This intimating couple between the velocity and the pressure, which is enable us to calculate the pressure field for a known velocity. Means one can estimate that how that pressure changes for a change in the velocity component of the time. Being this is up to this for the Navier-Stokes equation. Maybe slide number, if it is there, maybe 1920 of that kind. Here demonstration I'm not going to do right now. One can take these examples. I took it directly from some of the text actually. I'm sharing this with you, how that numerical problems can come if calculating the pressure field in Cartesian coordinates. Consider the steady flow, which is in two dimension, there is no doubt. For the incompressible velocity of for the fluid, maybe velocity v can be represented as u comma v. That must be equal to ax plus b along the I unit vector plus minus ay plus cx along the j vector. If this is the case, calculate the pressure, which is a function of x and y. How normally they will do? For a given velocity field, we have to calculate the pressure field. Means what assumption one has to make? Assumption one is that the flow is steady and incompressible. Means it is a steady flow. It should not have a turbulence. It should not have any days. And it is an being this, it is an incompressible fluid in the sense the expansion should not be allowed and compression should not be allowed. Fluid is an incompressible fluid and flow is a steady state flow. And the fluid has constant property. Temperature should not change, pressure should not change, density should not change. Okay, the flow is two-dimensional in the xy plane. Means if it is xy plane, w direction, z direction should be taken as the constant value. Gravity does not act in either x or y direction. Means x is along the direction of the flow, y is perpendicular to that horizontal flow. What you are expecting. Okay, but z direction either vertically upward or vertically downward, that is not taken with that one. Because of this, what happens? First, let us check here whether this given velocity field satisfies the two-dimensional incompressible and continuity equation we have to check. What is that? The expression you are expecting here. Here, del v del u by del x plus del uv by del y plus del w by del z. Yeah, this is the three equation del w by z. It must be equal to, you can call del u by del x as a acceleration, del v by del y as minus a, doesn't matter. Del w del z on two dimension, since it is a two dimension, third dimension is not allowed, this is equal to 0. If it is being a and a, this component, this must be equal to 0. What happens? Continuity is indeed satisfied by the velocity field because no change of the fluid if it is moving along the direction of the flow. You can't expect the horizontal flow. Along the v direction, there is no possibility of the flow. It will flow only along the direction of the flow. That's why only the A they have taken. Okay. If continuities were not satisfied, we should stop our analysis. Means the given velocity field would not be physically possible and we could not calculate a pressure field. Next, what happens being this? Consider the y component right now here in the Navier-Stokes equation along as far as the x. Rho times this equation here this equation, if you consider second one, rho times del v by del t plus u times del v by del x plus v times del v by del y plus w times del v by del z. This must be equal to the pressure, variation of pressure along y and variation of second term with the gravity, and mu times this is the coefficients. Being steady flow along the v should be 0. Being this u times velocity, u is the velocity, you can call ax plus b of that kind. This component you can call it as minus ay of cx. This is minus a. This is multiplied by minus a. This is the 0. Wherever it is crossed is 0 component. Okay, then which is the term we are having? Ax plus b times c minus ay plus cx times minus a. That must be equal to minus del rho by del y. If that is the case, y momentum equation is that this del p by del y must be equal to rho times here, take the rho as rho should be there here, rho is there actually, rho times minus acx minus acx plus minus bc minus a square y plus acx, or here two terms gets cancelled, rho times minus bc minus a square y. Means the momentum here in the equation here is satisfied if we can generate a pressure field that satisfies the equation as the rate of change of the pressure. In similar fashion, we can also generate the pressure along the x. Del p by del y must be equal to rho times minus bc, not along the a direction, minus a square y. Here minus a square x minus a times b minus a times b, okay, along the y x direction. Since the x momentum equation is satisfied, then if you can generate the pressure field that satisfies the equation 3. In order to satisfy these two, one can write this as a double derivative. Del square p over del x del y must be equal to del by del x of del p by del y, that must be equal to 0. Or del square p over del y del x here for the second equation, that is the third in case, del by del y of del p by del x is equal to 0. Here this equation what it shows is that del square p over del x del y or del square p over del y del x must be equal to 0. If we integrate this, it shows that the pressure is indeed a smooth function of x and y. Partial derivative is there. That the given velocity field satisfies the steady flow, which is also on two dimension, either xy or yx dimension, which is an incompressible Navier-Stokes equation. Means to say, if at this point in the analysis, the cross differentiation of the pressure were yield to the two incompatible relationships. In other words, if the equation in the equation 9.46, what you are expecting earlier, basic equation, were not satisfied, we would conclude that the given velocity field could not satisfy the steady flow or on two dimension, which is incompressible Navier-Stokes equation, and we would abandon our attempt to calculate the steady pressure. In order to calculate the pressure along x comma y, we particularly integrate the equation to here. Which one? Yeah, this one. We can integrate the equation to to with respect to y. There is no doubt. If we integrate that one, p of x comma y is equal to p times minus bcy minus s per y square. This is the constant of integration. Note that we added an arbitrary function here of the other variable x rather than a constant of integration, since this is a partial integration. G of x you can write. It is not a constant of something like that. We then take this partial derivative with respect to the x. Okay. We then take the partial derivative of this equation with reference to the x. What we will get actually, dp by dx, rate of partial derivative of x must be equal to g prime of x, or this gets 0. Root r, that may be equal to 0. If that is the case, rho times minus a square x here, minus a square x minus a times b, minus a times b, minus a times b, means cross differentiation of this in the xy plane. For example, p of x comma y is a smooth function of x and y only if the order of the differentiation does not matter. Then only we can call smooth. In the sense, either double derivative of the variable p along x comma y, xy, or maybe yx should be the same. For a two-dimensional flow field in the xy plane, cross differentiation reveals whether the pressure p is a smooth function or not. Means to say, where we have equated our equation 3 for the consistency here, this one for the consistency, and we now integrate this equation, this one 6 one, integrate this equation. What happens? Of course, this is obtained as a function of g of x. G prime goes to the d of x, rho times minus a square x over 2 minus ab times x plus constant of integration c. It is an arbitrary constant. Finally, if you substitute this equation 7 into the 5 as g of x here to obtain the solution for the p of x comma y must be equal to rho times minus a square x square over 2 minus a square y square over 2 minus abx minus aby plus constant of integration. What happens here? For practice, for example, as a chunk of our algebra, you should differentiate equation 8, there is no doubt, with reference to the x and y, both compared to the equation 2 and 3. See that this is equation 2 and 3. Okay, 3 we can differentiate, okay, this equation 8 with reference to the x and y. In addition to this, try to obtain equation 8 by starting with equation 3 here. Instead of 2, you can start with the 3. Rather than the 2, you should get the same answer. Of course, you will get the same constant of constant actually. This is how the fields can go. As an example, the velocity field in any incompressible flow is not affected by absolute magnitude of the pressure, but only a pressure difference. Means the velocity field, change in the velocity is not velocity is not dv by dt is not changed by velocity, particular for incompressible fluid is not affected by the absolute magnitude of the pressure. It is not depending on only the p value. It depends on the delta p. Delta p means the difference in the pressure between the two values. I will show you here right now. Assume that the atmosphere may be at a Bangalore atmosphere may be at a temperature of 900 hectopascal on daytime, and on next moment, next day, the temperature, sorry, the pressure difference may be about reduced by 10 hectopascal. Reduced, I am saying that 890. You will get the delta p. The change in the delta p is only 10 hectopascal. Either from 890 to 900 doesn't matter, or 950 to 940 doesn't matter, or 950 to 960 doesn't matter, or even only 400 to 410 doesn't matter. Delta p does not depend on the value of the p alone, but it depends on the difference in the p. Maybe for a particular location. I don't expect the change in the pressure over the Bangalore environment will go for less than 900 of that kind. This pressure appears only as a gradient in the Navier-Stokes equation. The absolute magnitude of the pressure is not relevant. Only pressure differences matters. Okay, that's why you see the example here on the right. Pressure is 9.22 gas here. This is the case. Here the pressure at the bottom is minus 3.562 gas. Okay, this is the entire thing, you can call it, because this is the low pressure, this is the high pressure. A parcel has to flow from high pressure to the low pressure. There is no doubt. If you push, the fluid has to flow and make some circle, okay, some shape of that kind. Here also, you take here, pressure is 509, here 496. About what is the difference actually? Still you are getting the same delta p. Means filled pressure contour plots, which is velocity vector plot. How that velocity vector in the sense how that fluid is moving in terms of its velocity plot, and a streamlines for downward flow of an air through a channel with a blockage. For example, here case A, case 1, and B is the case 2, identical to case 1. This is the case 1. This is the way case 1 and case 2. Okay, case 1 and case 2 of that kind. Okay, except P is everywhere increased by 500 Pascal. Here, P is increased by 500 hectopascal. On the grayscale contour here, which is there, okay, grayscale contour plots, dark is low pressure and light is high pressure. Dark color wherever you are accepting is low. Okay, light color is dark is low and low pressure, and light is the high pressure. Here, this high pressure. See that here, this is the high pressure going down. Dark is okay. Okay, this is also the same thing you expect actually. This one case, one example. Similarly, you can also calculate the pressure field in a cylindrical coordinate. Okay, how they will do? Just we'll discuss, then we'll stop. Consider the steady flow, two-dimensional thing, incompressible velocity field, or with a function of theta on t, which is equal to 0. This represents a live vertex whose axis lies along z coordinates. The velocity components are u of r must be 0 and u of theta must be k over r, and where k is constant. Calculate the pressure as a function of r and theta. The same function here. The analysis goes in such a way the flow field must be satisfy both continuity equation and momentum equation. Okay, for steady flow, 1 over r times d by d del by del r of ru plus 1 over r times del by del theta of du theta del by del z of this. These things gets cancelled. Means these are 0 because flow is a streamlined flow and velocity profiles for a line vertex of that kind. See that here being a thing, this is at the center point, this is at the outward, radially outward. The outward speed is quite high compared to the well inward at the radius vector. This can be given by an equation k over r. U of theta varies in such a way that u of theta comes down as the value of r increases. As the value of r increases, as the value. This is at the surface, at the center point. This is at the outward of the radii of that kind. Being this can be being an incompressible fluid. The continuity equation is satisfied. Now we look into the theta component, how it varies. There we got the second equation, first y component. Here instead of r component, you take the theta component. This is 0. This is some coefficient value. This is some coefficient value. This is another one. Being a 2-dimension, this is 0. That must be equal to this is 0. This is the value of that kind. If you solve for the momentum equation, particularly in terms of theta, okay, del p by del theta must be equal to 0. Del p by del theta must be equal to 0. Thus, the theta momentum equation is satisfied if we can generate an approximate pressure field that satisfies this equation. In similar fashion, the r momentum equation can also be reduced as del p over del r, that must be equal to r rho times k square over r cube. Being this, the r momentum equation satisfied if we can generate a pressure field that has to satisfy the equation. Being this, you will get the same thing, either del p by del square p by del r del theta, or del square p or del theta by del r. This is being a smooth surface. Being smooth surface, what this equation shows is that p is indeed a smooth function of r and theta. The given velocity field satisfies the steady flow. It also satisfies the two-dimensional. It is also being an incompressible fluid for the Navier-Stokes equation. This equation 1, if we integrate here with reference to theta, we will obtain the value of p of r theta. Earlier also we made the same thing. This being pressure field, which can form from the theta momentum, p of r theta or theta of r, you can got 0 times g of r. This is one more variable we have put. This after integration, differentiation, you will get del p by del r. It is a constant of differentiation. You can get, you will get rho times k square by r cube. Means for a two-dimensional flow field in the r theta plane, cross differentiation reveals whether p is a smooth function. del square by del P over del R del theta, or del square P over del theta del R remains constant. Being this G of R you estimate after integration this one, G of R is equal to minus 1 over 2 times k rho times k square by R square plus constant of integration. If you do it, C is the arbitrary constant of integration. Finally, we substitute this equation into this 4 where G of R is required. If you do that, P of R theta must be equal to minus 1 over 2 times rho k square by R square plus C will get. Okay. Thus, the pressure field for a line vortex here, for a line vortex, what you are expecting for a line vortex works like, decreases like 1 over R square, inversely proportional to the square of the distance as we approach the origin. Means from this point, as you go on approaching the R is this point, we have to come here. Okay, or means as you are approaching the 1 over R square, R increases, means as we are approaching the R square, this function decreases. This function decreases. Means what function decreases? U of theta will decrease. U of theta is maximum at the near. As you are approaching the R, actually, this function will decrease. This function will decrease. Sorry. Yeah, here. This function decreases. This flow field is a simplistic model of the example of tornadoes or hurricanes that I will represent in next figure. See that tornado and hurricanes, how it works. Just I'll see that. I will describe. Okay. We note that here this flow field is irrotational, and thus the Bernoulli equation, what we got it earlier for the fluid dynamics, not discussed in our class, can be used as the instead of to calculate the pressure. If we recall the pressure at infinite distance, but away from the origin, where the local velocity approaches zero. Bernoulli equation shows that at any distance or from the origin, the Bernoulli equation represents P plus P pressure plus 1 over 2 times rho square V, rho times P square must be equal to P infinity, or P can be represented as P is equal to P infinity minus 1 over 2 times P is equal to P infinity, P is equal to P infinity minus, take this on the right side. What equation 8 here says that with our solution on the 7 here, this equation 8 agrees with our solution on the equation 7 from the Navier-Stokes equation if we set a constant, this C, which is equal to P infinity. P infinity, C becomes P infinite. Means a region of rotational flow near the origin would avoid the singularity where there would be a more physically realistic model for the tornado. If the discussion goes in such a way for this expression, try to obtain this equation 7 by starting equation 2 rather than from the equation 1. You should get the same answer. Earlier also we made the same case. Here, this is the generation how it can start like tornadoes. This is the force. If the two forces are of that kind, continuously going up, 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 up. Pressure P is along this direction. This is the radius vector. And the total force, how it has to go? It has to go in the green color. Green color, you can see that at least. Okay, is the two-dimensional vortex which was formed in the atmosphere as a simple example or the approximation similar to that of a tornado. The lowest pressure is the center of the vortex. Here, this is the center of the vortex, is the lowest pressure. As you are coming outward at any point, it should be increasing. What must be the pressure? Pressure should be having infinite. It might have reached the saturation value. See that here it is the lowest value. It goes up, 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 and gets saturated at the periphery. Means like coming up, saturates at the periphery. It moves with the constant. From the bottom or from the tip of this bottom, as it evolves as the higher pressure, as it enters into the upper atmosphere or at greater heights, the energy gets energized or excited. This is an exact solution of the continuity equation. Maybe through boundary condition, they are saying that. I'm not discussing, but I will leave this example to you to understand within the slides. And this is another example actually. Take it as an exercise and try to understand the problem. Maybe simpler thing. This is another example. This is another example. Some other 5 problems I am giving actually. This is another one, 6th problem. Or you can stop at that point. Okay, we discussed about some 3 differentiations. Equation of the day is that del u by del t must be equal to v square, v times del square u by del x square. I'll stop at this moment. If you are having any queries, I'm happy to answer to your query. I'll stop sharing the screen. Thank you. If there are no queries, I will continue the class by 11 o'clock according to your schedule. Aparna, Arpita, Lavanya, Monisha, no queries? Looks like complicated equations. Don't get worried. We try to practice this one. Quickly text. Shall we stop? At least one yes or no?
Yes, sir.
Okay, thank you. I'll end the meeting right now. Class. We'll meet next class.